Good afternoon. I'm Dan Freed, Director of the Harvard Center of Mathematical Sciences and Applications, the CMSA. So it's my pleasure to welcome you here for this annual Ding Shum lecture, generously funded by Ding Lei and Harry Shum. The CMSA is a mathematics center on campus, which engages in the two-way interaction of mathematics and science. We run different month-long programs, different workshops, different conferences, weekly seminars, and a few special lectures, of which this is one. So today we're delighted to have Irit Dinur from the Institute for Advanced Study, and she'll tell us about expanders from local to global.
Okay. Thank you. Thanks for the invitation, and I'm very happy to be here. And I'll talk about expanders. I'm not sure what is the mix of the crowd, so please ask me questions or speed me up in case it's a bit slow. We'll see. Yeah, that never happens, right? Okay. So I want to tell you about expander graphs. In the slight chance that maybe you don't know what a graph is, maybe I'll talk about graphs first. Okay, so it's something we all know. It's basically just networks, and we have a lot of networks around us, like biological networks. This is a picture of some biological network where you have vertices that are corresponding to proteins, and you connect two by an edge if there's an interaction between this pair of proteins. And that's a very useful way to study various pathways in the body, to look at such a graph. The internet is a network we all know. In this graph, I'm not even sure where I copied this from, but presumably every node is like a web page, and you put an edge if there's a link from one web page to another, or something like that. Oops. Okay, here's another network of roads where you put a node for important locations, and you connect them by an edge if there's a road segment between them. So there's many, many networks all around, and graphs are a natural mathematical abstraction to study some of their properties. Okay, so what is a graph? It's just a collection of vertices. They're just, we draw them as these little dots, and edges, which are pairs of vertices. And it doesn't really matter how you draw them. What's important is which pairs are connected and which pairs aren't connected. That's our graph. And they offer us a way to understand objects by removing a lot of the extra information and focusing just on the information in the graph. So objects outside of mathematics, but also inside mathematics. A lot of objects are nicely understood when you look at the graph aspect of them. So for example, in geometry, maybe you have some complicated geometric space, and you describe it by a discretized graph, and that gives you some interesting information. Even a system of equations over variables is sometimes, you'd be surprised, very useful to study as a graph. You would maybe put variables on the vertices, and an equation between two variables would be represented by an edge. So somehow that's useful. Sometimes we study groups, like in group theory, by looking at graphs that represent some aspect or some structure of the group. So for example, think of the group of all permutations on n elements. That can be a very, very large group, even for small n. And you might want to understand things about this group by looking at related graphs. We'll see in a minute. So here is a picture of how to view a system of equations in terms of a graph. I basically have a lot of inequalities. And for every inequality between two variables, I put an edge in the graph. You might think that it's weird to just look at equations that look at only two variables, but somehow you can always have equations that look at more variables, and that will give you higher dimensional graphs. like hypergraphs. And we will get to that towards the end of the talk. Anyway, this is one example of, instead of thinking of the equations in other forms, you just think of the structure, and the graph kind of tells you a geometry of the set of equations. Okay, here's another place where we think of graphs in math for random walks. So here the question is, you have a deck of cards, 52 cards, and you want to shuffle it to get a random deck. What's a good way to do it? Okay, so there's a lot of different ways to order 52 cards. It's really a huge number. My clicker is not so efficient. Okay, so basically what we want here is to get a uniformly random permutation out of the 52 factorial permutations. And the way we usually do it in life is by shuffling. The picture here shows something called the rifle shuffle. And when you try to analyze how good is it, how close does it get you to actual uniformly random permutation, then one way to analyze it is to think of the underlying graph. So what is this graph? In this graph, which we imagine in our heads, we have a vertex for every possible way to order the cards. So 52 factorial vertices. And it's not like I'm saying, let's program this on our computer, because the number of vertices in this graph is more than, I don't know, the number of atoms on Earth. But nevertheless, you can think about this graph, and you can connect one vertex to another if there is a rifle shuffle move that will move you from this order to that order. Okay, so you get this graph. And now, what does it mean to do a sequence of random shuffles? If you think of it in terms of the graph, it's as if you start from some arbitrary location, whatever your deck of cards happens to be in right now, and then you take a random shuffle step. So it's like moving to a random neighbor in the graph. And then you repeat this a few times. So it's like taking a few random steps in this graph. And you can ask, for this specific graph, how many steps do I need to take so that the probability distribution is kind of close to uniform on this entire graph? And it turns out that for the rifle shuffle, 7 steps, I think, is enough to get you close to uniform. You can even think of a simpler type of shuffle where instead of cutting the deck in a random location and then shuffling, you just take the top card and insert it in a random location in your deck, so that you have like 52 or 51 different possibilities. And then you would get a graph on the same number of vertices, but every vertex is now only connected to 51 other guys. So pretty sparse compared to the 10 to the 60-something vertices. And yet, when you analyze random walks on this graph, it turns out that in something like 200 and something steps, you converge to uniform. I think that's quite amazing, considering the huge size of this thing, that in a bounded number of steps, you get to a random deck. And what's going on underneath the hood here is that this graph is an expander graph. I want to define what that is. But one way to think about it is it's a graph that on one hand, it's pretty sparse. But on the other hand, very quickly, when you take a random walk in this graph, you might land anywhere. There's no area in the graph that you, even though you take random steps, you get stuck inside this area. You always go out. Okay, so let's define expander graphs. Okay, so a graph is an expander if it is very well connected, and we always think of sparse graphs. So one way to think about, to formalize it, is to say that random walks mix well, mix fast. Another way is to say that in this graph, no matter how you choose a small set of vertices, it will be very outgoing, okay? Not a lot of edges will stay inside this set. Most of the edges will go out. Okay, so it's a graph that doesn't have, you know, like introverted communities. All the sets of vertices are very well connected to the outside. And these definitions are equivalent, and they're also equivalent to another definition which says, look at the adjacency matrix of this graph, look at the eigenvectors, and there's a good spectral gap between the top eigenvalue and the one after that. But I'm not going to get into this kind of technical detail. Okay, so are all graphs expander graphs? The opposite, well, it's not true that the opposite is true, but there are many graphs that we know that are not expander graphs. In fact, the graphs that maybe you see around you at first sight, they are not so expanding. For example, like the graph of roads or the geometry that we are used to, like Euclidean geometry, is not an expanding geometry. So let's look at this graph. It's very sparse. Every vertex here has only 4 neighbors. And don't worry about the boundary. If you want to be completely regular, you can imagine that every vertex at the top is connected back down. And you kind of fold the graph into a torus. So then it's completely symmetric. Anyway, look at this graph. I'm saying that it's not an expander. What's a good way to see it? You can look at the set of d-squared vertices, okay, like a d by d part of this grid. The number of edges going out is 4 times d. But the number of vertices there is d squared. So the number of edges is d squared times some constant. So most of the edges stay inside, and only a tiny fraction of the edges go out. So this is an introverted community, right? You don't have a lot of chance of leaving. Question? Okay. Okay, so this is not an expander. So do expanders even exist? So a famous thing in theoretical computer science is that the first time people thought about expanders, they were thinking about it, trying to prove that they don't exist, with the hope of actually using that to prove some lower bounds in complexity. But it turns out that they do exist, and Pinsker proved that, in fact, almost all graphs are expanders. So just to say exactly what I mean here, if I fix some parameter d, like 10, and I look at all graphs on n vertices for any n that are d-regular, so every vertex is connected to exactly d other vertices, you look at all possible such graphs, a huge amount of them, almost all of them, will actually be expanders. And this is proven through the probabilistic method, so it doesn't really give you a way to get an expander in your hands. And you can ask, okay, but give me one that you can construct with your hands. So we have such. The first such families of expanders are actually Ramanujan expanders, so they actually have some optimal behavior. And they come from number theory. So people who came up with them thought about these graphs because they were thinking about something completely different. They were thinking of a graph that is infinite. This is the infinite tree. What you see here in the picture is the infinite 3 regular tree. So you have a vertex, and it has 3 neighbors. And then each one of these neighbors, it already has 1 neighbor, this vertex, so they have 2 more neighbors. And then each one of them have 2 more neighbors, and so on, all the way down. Okay, so it's an infinite graph. It's an infinite tree. And you can view this tree as if it's a graph of some group. Just like before we thought of this graph of all these decks of cards as a graph of the group of permutations, this graph is also a graph of a group. You can associate a group element to every vertex in this graph. And then if you look at a subgroup of this group, it will give you a way to color the vertices of the graph in different colors, depending on which coset of the subgroup you are. And then you glue together all the vertices of the same color, you get a finite graph. So maybe what I said is a bit technical, doesn't matter. The point is you can kind of glue the infinite tree onto itself in a way that gives you a finite graph. Now, why is this useful? Before we did this gluing, if you just look at this tree and you think about taking a random walk, suppose you start from the center, from the root. You know, in an infinite tree, every vertex is the root. There's no difference. You start from some vertex, you take a random walk, you see 3 new neighbors. Then you take another step, you see new neighbors. So you're always going to see new things. There's never a wasted step. You see, kind of, you expand maximally. So in that sense, the infinite tree is like the best possible expander for random walks. And what is proven about this quotient of this infinite tree is that it's also very optimal in some spectral sense. Okay, so this is these Ramanujan expanders. Now, even though the Ramanujan expanders come from an infinite object and the quotient is kind of complicated and the proof that they're expanders is very hard, the actual graph that they end up describing is very easy to describe, and you can find online many implementations, excuse me, of this graph. So it is explicit, but the proof kind of is very difficult. So it is unsatisfying in some sense. And this is maybe one of the reasons that drove Reingold, Vadan, and Vigdorson to try to find a more elementary construction of expander graph, something that doesn't require any infinite objects or any specialized knowledge in number theory. And there is this iterative algorithm that takes small expanders and puts them on some other expander and kind of keeps growing this expander iteratively. So by now, we really have a lot of constructions of expanders, and it's a really well-developed topic, many applications. It's really well understood. Inside of mathematics, there are many, many applications for expansion. You study it when you think about isoperimetry. You study it in geometry, in group theory like we saw, convergence of Markov chains like we saw a little bit. And also in computer science, there's a huge list of applications in different areas where expanders are used, which I won't talk about all of them. I just want to talk about one aspect of expansion, which is this ability to lift the local properties to global properties and how it's good for resilience to errors. Okay, so this is the topic I will focus on today. The infinite tree looks like fractals, that's true, but the finite expander is not really a fractal because it's a finite thing. You can say that in some ways it behaves like the infinite fractal thing, but I don't think it's quite the same. By the way, please ask questions. Don't be shy. Okay. Okay, so what am I going to talk about? So we finished our introduction to expanders, and I'm going to talk about two topics where expanders come in. One is the topic of error-correcting codes, and one is the topic of probabilistically checkable proofs. So basically, in both of these areas, expanders kind of are used to get some desirable object, some desirable resilience to errors. But both of these things are going to be results that are known for at least 2 decades. In the last part of the talk, I will talk a little bit about new things, but not too much. Okay, so error-correcting codes. I'm not assuming we know what they are, so let me give a quick introduction. So suppose you want to transmit some message, maybe a bit, and there is going to be noise, so it's not clear that your bit will get to the other side. So maybe you want to transmit 0, but then something happened and the bit was flipped. So what would you do? I mean, what I do when I try to transmit messages in my house is I just say it again. So you transmit the bit 3 times. Okay? And then if only one bit got flipped, then the receiver that gets the 001 can just take majority, right? And recover the bit that I wanted to send. Okay, so that's not so bad, but it's a bit, okay, that's the recovery. It's a bit wasteful. If I want to transmit 1,000 bits, I need to send 3 times that number of bits. So that's a bit expensive, but much worse than that. Suppose I transmitted this 3,000 bits and 2 errors happened. It might have been that it's the 2 errors just on the same repetition of the same bit, and that bit got lost. Okay? So even though I'm transmitting 3,000 bits, I didn't manage to protect a specific bit in my message from 2 noise flips. And when we transmit messages, most of the bits are not so important, so you don't need to be obsessed about every single bit. But some bits are actually very crucial, like if it's the plus or the minus in your bank statement, that's a very important bit. So we really want to encode so that we protect every single bit from being flipped. And this is really what the theory of error correction is all about. It's a huge theory, and I want to tell you just a little bit about it. So there is a very simple and very, very powerful idea, which is instead of just repeating bits, you use linear algebra. You transmit your message, and then you add some more parity checks. So what is a parity check? You choose some subset of the message bits, let's say all of them, and you see if the number of ones is 0, is odd or even. If it's odd, you transmit a 1. If it's even, you transmit a 0. So that's a parity check. And you can do it for other subsets of the message bits. In other words, you're computing a linear transformation of your message over the field F2. Okay, so here is an example. This matrix that you see up there is a matrix corresponding to a code that takes 4 bits of message and encodes them by 7 bits. So it adds 3 parity check bits. And you can see that the first, so here the message is 0, 1, 1, 0. And you can see that the first 4 bits of the encoding are the message. So you just copy the message, and then you add 3 more bits corresponding to this matrix. And kind of interesting thing is that every 2 encodings in this code are quite far apart. How far? They're at least 3 bits apart. Okay, so we have here a linear space, which is the image of the message space. It has 16 different code words, and every pair of them are at least 3 bits apart. That's quite cool, and it allows you to recover from a 1-bit flip, because if I sent you some code word and then some error happened, you get some string that's not in the code, but there's going to be a unique code word that's only 1 bit away from you. So that's a pretty nice thing. And in fact, this generalizes. If you wanted to encode a k-bit message by n bits, you can just choose a random linear subspace. And what you need to ensure is that in this linear subspace, every 2 elements are quite far apart. So you want them to have many bits to flip, to move from one code word to another. That's called the distance. Okay, you want in this subspace to have a large distance so that every pair of code words are that many bits apart. Okay, so I said that random subspace will give you a good solution. That's true. But if you use a random code, it's true that if you send me an encoding and some bits happen, there will be a unique closest code word. But the question is, how will I be able to find it? I need to have an efficient algorithm to be able to find this closest code word. And for random codes, this is not conjectured to be possible. So there are other ways, and expander codes are one of the other ways. And I want to show you how to use expander graphs to achieve this. And the reason I particularly like this is because it's natural to think that expanders are useful for network routing, and they're very connected. So they're useful for, if some edges fail and you can still find a path around. So that's kind of natural. But the fact that expanders can be used for coding, that's kind of unexpected. Or why would linear algebra connect with expanders? Okay, so here is a naive attempt. It won't work, but it will kind of warm us up a little bit. So first attempt is to construct this linear subspace. So what I'm aiming to do is to construct a subspace so that every 2 elements in this subspace are far apart when I measure distance in how many bits you need to flip to move from one to the other. So let's look at an expander graph, and let's look at the incidence matrix of this graph. So it's a matrix that has V rows for all the vertices and E columns for all the edges. And I'll just look at the kernel of this matrix. So basically, my code will be all the strings whose coordinates are indexed by edges, so that they're in the kernel. What does that mean? It means that for every vertex, if I look at the edges that touch this vertex, and I look at the coordinates in that string, these sum to 0 modulo 2. Okay, so I think it's better to look at the picture. So here is a graph, and the potential code words, I think of them as if they are labeling each one of the edges by a 0 or a 1. So think of such a labeling of all the edges. When will this thing be a code word? If for every vertex, if I look at just the edges touching that vertex, their sum, or the number of ones that I see, will be even. Just the sum modulo 2 is 0. That's the definition for this code. Now I want to ask myself, is this a good idea? Did I define a code that has good distance? So I need to know whether or not there are two words in this code that are too close together, or whether every pair of words are far apart. And the answer is that there are actually words that are quite close together, because you can think of one word being the all zero string, that's always in my code, and another word being a word that has all zeros except for ones on a cycle in the graph. So think of any cycle in this graph, put ones just on those edges and zeros everywhere else. Then every vertex that doesn't touch the cycle, of course, it will see all zeros and it will be happy. And every vertex that's in the cycle will see just two edges, right? So the number of ones it sees is even, so it will also be happy. So this code is indeed just what's called the cycle code. It's spanned by all the cycles and some modulo 2 sums of cycles. So why is this bad? Because in an expander graph, you always have cycles of length logarithmic. Okay, so really the number of ones distinguishing a cycle from the zero code word is just logarithmic. It's not linear like I would like. I would really like to find a code that the number of ones is either 0 or at least linear in n. Okay, so this was a naive attempt. And then what did Zipser and Spielman suggest? A very simple fix. They said, well, I already know that I have codes that have a linear distance, and let me fix some such code on d bits. So suppose my graph is, unbound, it's very large, but every vertex is only connected to d edges. Then let me fix a code just on d bits, and suppose that this code already has some distance. So I know that in C0, this fixed code, every two code words have at least distance of delta 0 times d. Okay? Now I'm going to use this small local code to define my big global code. And the definition is very similar to before. I'm going to allow all labelings of the edges of my expander, but my condition will be that if I look at any vertex and I look just around that vertex, I see basically a substring of the entire string, right? Because the entire string describes the labeling on all the edges, and I'm just looking at the substring corresponding to the edges touching V. I want this substring to be in C0. And for every vertex, I make this requirement. That's the definition of the code. So basically what we did here is we defined this global code on E coordinates by using a local code just on D coordinates and putting it all over the place for every vertex. I think that's a very nice definition. Now, what does it buy us? Well, here is the picture. Now, remember, my requirement is that for every vertex, the substring around it is in the small code C0. So by the way, I guess this is the most technical part of my talk. So I'll let you know when we're done with this in case I lose you. I apologize. Okay, so I want to convince you or prove to you that in this definition, in this code, every non-zero code word has a lot of ones. And I'm also claiming that it means that no two code words are close to each other. If I have two distinct code words, then their difference is also a code word because it's a linear subspace. And so I can look at how many ones this new code word has. And that tells me exactly how far apart these two original code words were. So all I need to worry about is whether or not I have words in this code with too few number of ones. Okay, so let's think about some non-zero code word in this code. So it has some edge that is labeled by 1. Now look at one endpoint of that edge, some vertex. It sees at least a single 1, and you know that whatever it sees locally must be in the small code C0. So actually, it's not only a single 1 that it sees, because there must be at least delta 0 times d different edges that have 1s on them. So it means that this vertex has at least delta 0 times d neighbors that themselves see a non-zero edge. Okay, so now let's move to any one of those. From the same reasoning, they also have delta 0 times d neighbors that have a non-zero edge, and so on and so on. Okay, so because of the expansion of the graph, this kind of propagates and it goes all over the place. And if you want to hear something slightly more formal, think of just all the vertices that touch a non-zero edge, okay? If this set is small, if the number of non-zeros is small, the set is small, then you have found a small community that's very introverted. All the ones are inside and none of them go outside. And we said that that's by definition not possible. Okay, so we are done with this proof. Okay, so basically we found a way to prove distance for this code by a local to global argument. We used the local distance of C0 and managed to deduce global distance of the entire code. But I think that's kind of Say again the question? Oh, yes, thank you. Sorry, I didn't say anything about lambda. The formal statement is exactly this. Lambda is the second largest eigenvalue normalized divided by d. And this is the exact statement. If the small code had distance delta naught, the new code will have distance at least delta naught minus lambda. And it's really very simple to prove if you feel comfortable with eigenvalues. More questions? Okay. All right, so we did error correcting codes and we saw how expanders play a role in them. Okay, where are we standing? Okay. So now I get to talk about probabilistically checkable proofs. So before I talk about that, let me say something about the P versus NP question. Okay, it's a very important problem, and it's it's fundamental also philosophically, not only from a math perspective, because it says something about what we can compute actively compared to what we can check passively. I mean, if you tell me something and I only need to check it, it feels very different from if I need to find it out myself. But we don't know how to prove that these are really different. We conjecture that P is not equal to NP. And really, this whole area of computational complexity is interested in this question, among other questions. Interested in understanding what problems are easy, what problems are hard, how to distinguish between problems that are easy or hard. So understanding really like the limits of different resources. And part of one direction in which we try to approach this question is through the PCP theorem. The PCP theorem says that if we assume that P is different from NP, then there's a bunch of problems that we know are hard. And it shows that many additional problems are also hard. So it's like looking at a lot of problems that you might think are easy, and the PCP theorem tells you, no, they're actually very, very hard. So in some sense, it's pushing the boundaries of this class of difficult problems. Okay. Okay, so it's really considered to be a very celebrated theorem proven in the early 90s. And what does this theorem say? It says that if you have any NP statement, so if you don't know what an NP statement is, just think of any computation. It has a proof. You can show me kind of how the computation went step by step, just doing the computation for me step by step, and proving to me that the end result is whatever you claim it is. That's kind of the natural, obvious proof. But what the theorem says is you don't have to do it that way. There's a different kind of proof that we're not saying what it is, but it exists. And in this new proof, you can check it just like you would check the kind of normal thing where you just imitate the computation step by step. But this time, you can check it very efficiently. What does it mean very efficiently? You don't even need to read most of the proof. You select a random step and check just that random step. Okay, that's what the theorem says. So this sounds quite crazy because we know that if there's a bug, it can be hidden in a very subtle location. And if I don't check all of the proof, I'm going to miss the bug. Right? So how can this theorem even be true? So the thing is, you shouldn't think of a proof as a sequence of steps that's like a linear sequence, but rather something different, and we will see in a minute. But of course, okay, we just said that it's quite counterintuitive. Proofs, we usually think of them as very, very fragile. So you ruin them in one place and they get ruined. Somehow PCP proofs are not like that. They're very robust. So even if you ruin them in some 5% of the location, the fact that all the other checks are good means that the proof is correct. So in that sense, it's similar to error correcting codes. You have some noise, but still somehow the computation is robust. So if it's even 95% true, it's true. Okay. And it also, in addition to just being kind of an astounding statement, it also has a lot of applications to different areas, most prominently to the area of hardness of approximation. So I will talk about it in a minute, but this relates to what I talked about before about pushing the boundaries of NP. Problems that we think are hard, we might try to weaken them and say, well, finding the exact solution is hard. Why don't I just try to approximate? That seems like a much easier task. And it turns out that through the PCP theorem, many approximation problems are also hard. And additionally, in the past few years, it turned out that many real-world applications actually rely on the PCP theorem. So if you think of various tasks to do with cloud computing, suppose I want to do some very complicated computation, and my cell phone is too weak for that. I send this computation to the cloud does the computation for me, and it gives me back an answer. But in many situations, I can't just believe it. I need to check that this computation was correct. So how would I do that? If I need to go over every step, I don't need the cloud at all. So the whole point with the PCP proof is that I can check randomly, right, in kind of a random location and need just very little communication. So indeed, there are a lot of companies out there that are now implementing PCPs for blockchains and other things. And from a personal perspective, when I was a graduate student and I started learning about PCPs, I thought they were just fascinating because they both have really nice mathematics, and they talk about something very fundamental, like about the nature of proofs, how randomness affects verification. So they allow you to talk about semi-philosophical things and in a very rigorous way, and do math at the same time. And I just loved it, and I think it's really a beautiful area. But friends of mine asked me, what are you doing? And I was telling them, and they said, well, can you implement it? Can you use it? And I was thinking, these people totally don't understand what they're talking about. Okay, so 20 years later, 25 years later, these things are being implemented. So I find it kind of very satisfying, although I have nothing to do with that, but still. Okay. All right, so I want to tell you a little bit about the PCP theorem from a more technical point of view, to tell you more accurately what does the theorem say. And to do that, maybe a good way to describe it is to think of it as a hardness of approximation statement. So I have here a picture of a system of equations which I describe as a graph. Remember, I have a variable for every vertex, and every edge corresponds to an inequality saying, this vertex's value is different from that vertex's value. And really what's described here is something we call the three-coloring problem. It's the problem of finding an assignment to each variable from three values, 1 to 3, or red, white, and blue, or who knows. And you want to satisfy all of these inequalities. Okay, so this is a problem, a computational problem. You can go over all possible solutions and see if there exists one, but that would take you exponential time. And it turns out that this is an NP-hard question. So what does it mean that it's NP-hard question? Firstly, we don't expect there to be a polynomial time algorithm for finding a solution. But more interestingly, it means that any other NP computation can be recast and expressed in this form. So this kind of weird, esoteric-looking programming language of writing a graph and a bunch of inequalities expresses any computation. Okay, so I mean, okay, maybe it's not so intuitive to see it, but just, you believe that many different programming languages are similarly expressive. This is a very expressive format, apparently. Okay, so any NP statement I can write in this form. And I know that it's hard to decide if a given system like this is solvable or not. Now I can ask for a weaker solution, weaker problem, which is, okay, I don't want you to solve all the equations. I'm interested to know whether there is a solution that satisfies 99% of the equations. So I'm willing to allow you to violate some 1% fraction of the equations, but I still want a solution for the most of the equations. How hard is this problem? Okay, it seems to be much easier. And indeed, it depends on the number. So now it's like it's a question of the 99%. If you reduce the 99% further down, like to 90%, then actually we know how to do it. There's a polynomial time algorithm. But if you keep it at 99%, I think if I'm not mistaken with the numbers, I think it's NP hard. So let's not focus too much about the number. What the PCP theorem says, one way of framing it, is that given a system of equations, there is a way to encode it by a new system of equations so that now the new one is hard to even approximate. So if the previous one was perfectly satisfiable, the new one will also be perfectly satisfiable. But otherwise, if the previous one was not perfectly satisfiable, for a system of equations, maybe there is a solution that solves almost everything but fails on one equation. That could be. In the new system, that cannot be. If the new system, you are promised that either it's perfectly satisfiable or there's going to be at least 1% of problems. Okay, so that's what this, one way to view this theorem. It's a kind of encoding. It doesn't encode just bits into bits. It encodes equations into equations, something like that. Okay, so just like before in the error correcting code setting, we encoded a message into an encoding and we could tolerate some amount of errors. Here we're encoding equations into a new system of equations. And what this tells us is that if you had an approximation algorithm for this problem, you could solve exactly the original problem, because you would first do the reduction, then run your algorithm in the new system, and that would decide 3-coloring. Okay, I feel maybe I lied about the error correcting code being very technical, because this maybe was also technical. So, okay, let me try to tell you something about how to prove this theorem, basically how to transform a system of equations into something that is even hard to approximate, but I'll only give a very, very high level. So basically, this is a proof that proves the PCP theorem using expander graphs. And the whole point of this sequence of results was to show you how expanders appear in these maybe unexpected places. So the idea was you take this graph and you break it into small pieces. Here the pieces are, you take a vertex and you take all the equations connected to that vertex. Okay, so these are my small pieces. And then, just like before, we had a local code that we maybe found by brute force or for some reason. Also here, I'm imagining that I already have a PCP that I can run on something of constant size, just again, by having PCPs that are inefficient, but if you run them on a 4-bit system, it just causes a constant blowup. So now I basically run a PCP separately on each piece. And this PCP makes sure that you give me an assignment to the variables in that piece that satisfy all the equations in that piece. And now all I have to do is to put them back together, make sure that the assignments to the different pieces match together. And of course, if there was some problem and this whole system was not satisfiable, there's no way for you to do that. And the point of the expander, and I can't explain the details here, that the problems will grow. Okay, somehow, because you're all in an expander, if there was some problem, it will propagate further out. Okay, so I'm also cheating a lot. You need to repeat this many times. But after you do that, the resulting system of equations got this gap amplified. Satisfiability, if you started with something good, it stays good. But if you started with something that had a problem, after one step of this transformation, there's more problems. And if you repeat it again, there's even more problems, and so on. And in the end, you get this amplification. OK. So this proves to you that the new system is hard to approximate. And what does that have to do with writing a proof and then checking it very efficiently? So the connection is actually very simple. If you started with an NP statement and you want to prove it to me in a way that's easy for me to verify, what you need to do is first express it as a 3-coloring problem, then run this reduction, and then give me the proof for this new system of equations. And then I can just randomly select one of the equations and check if it's satisfied or not. So it gives me this random verification. OK, so this is my last slide on PCPs. Basically, you have here this whole area of hardness of approximation. I only gave you one tiny part of it. It's a very well-developed area. There's also a lot of practical applications, like I told you. And if you think about it, what is a PCP? It's really a local to global object. It tells you how to encode any NP statement. That's a very global object in a way that you can check it using very local checks. So you basically allow local checks to deduce some global statements. So it's very naturally fitting into this expander world. OK, so in this theory, we are interested in better parameters, shorter. Recently, people study interactive PCPs. So there's a lot of kind of activity going on in this area, and we're looking for new and different constructions. And this is leading me to the last part of the talk, which is high-dimensional expanders. OK, so as I said in the beginning, the first two topics that I talked about, error-correcting codes and probabilistically checkable proofs, the results that I described are quite mature by now, let's say. Let's not say old. But this is a newer area, high-dimensional expanders. It's basically a new kind of expanders. And it's kind of very intriguing, and I want to tell you a little bit about it. Again, it's quite technical, so we're trying to just give a little bit of feel. OK, so what is this area? So a graph, we said you have vertices and edges. What is a higher dimensional graph? Basically, you have vertices, and instead of edges just containing 2 vertices, maybe the edge contains more than 2 vertices. So it's just a hypergraph. OK. In the past, there have been many different definitions of expansion for hypergraphs. It's natural to try to extend the old definition for graphs to the world of hypergraphs. But somehow they were useful in some directions, but not in the directions that I care about with relation to PCPs, for example. And it turns out that from number theory, the same area that gave us the infinite tree and the quotients and the expander graphs, they also have a high-dimensional analog for their infinite tree. Okay, so just like they have an infinite one-dimensional tree, they also have the same kind of thing, but in higher dimensions. And it so happens that this gave kind of a clue to a very different direction of defining expansion. Okay, so this is the picture of their 2-dimensional tree. So I don't know if you can see much from it. What we see here, you can think of it as you start with a triangle, and you think of it as like a face. So it's like a 2-dimensional object. And then on every edge, you glue many other triangles. And then on those triangles, for every edge, you again glue many other triangles, and so on and so on. You get something. And really what I'm talking about is something called the Brotitz building. What is this object? It is an object that appears when you study certain p-adic groups, and it's very important in number theory. And then you use this object to say that your groups act on this object, and it, in some sense, it replaces, you know how groups over the complexes work over the complex vector space. So these p-adic groups work over this strange Brotitz building. But so, of course, when this was developed, they didn't have computer science in mind, and yet somehow this object has some really interesting properties. So Lubotsky, Samuels, and Vishne decided to try and construct finite quotients of this object in analogy to how finite objects of the infinite tree gave expanders. And they succeeded. And then they got this object that they called Ramanujan complex, just like before it was a Ramanujan graph. So they have this Ramanujan complex, and I think especially Alex Lubotsky just thought that he has something really amazing in his hands, and he just tried to convince other people to look at it. And I think he succeeded. So in I think groundbreaking work with Kaufman and Kashdan and Lubotsky, they wanted to prove some property about this object, some topological overlapping property. But while trying to prove this, they how do you even get at it? It's such a complicated object. So they described what the object looks from a local perspective. Basically, they described if you fix a vertex and you look at all the triangles touching this vertex, it's a finite number of triangles, even in the infinite Brotitz building. And then what you see is if you remove this vertex from the triangles, what you remain with is just a graph. And this graph is an expander. So that's how they gave this definition of what it means to be a high-dimensional expander, that every link, this is called a link, is an expander. Okay, so maybe I have here their definition. They said if you have a big complex, the link is just a local piece. It's like the neighborhood of a vertex. But unlike in a graph where the neighborhood is just a bunch of isolated vertices, in a two-dimensional complex, the neighborhood itself has edges. And so in a high-dimensional expander, one definition is that this whole thing is locally an expander. Every link itself is an expander. Okay, that sounds like an okay definition until you think about it some more and you realize, I myself don't know of a single way to construct such an object with small links. Somehow, whenever you try to do it, you want to make your link sufficiently well connected, but then you cause more neighbors to other vertices, and the graph becomes dense. Nevertheless, using this Brotitz building and other algebraic constructions, you can get objects that have expanding links. And then they have these fantastic properties. For example, there is this theorem by Oppenheim, which is the trickle-down theorem. It says if every link is an expander, then the entire connected component is an expander. So it gives you a local condition for global expansion. That's one theorem that I think is very nice. And once you have this definition in your mind, you can also look at other objects and understand that you can analyze different objects using this framework. So there is this beautiful work that resolved a long-standing conjecture about convergence of certain Markov chains. So here you have some matroid, and you're trying to sample a random basis in this matroid. So let's be more concrete. Suppose you have a graph, and you want to sample a random spanning tree in this graph. So what is it similar to? It's similar to when we described how to shuffle a random deck of cards, and we wanted to reach a random permutation. So here we want to reach a random spanning tree in a graph. So what this result of Anari, Liu, of Esgaran, and Vincent says is that the natural random walk, which I'll tell you what it is, converges. And what is the random walk? You start with some spanning tree, and then you erase one of the edges, and you add some other edge at random that makes it into a spanning tree. And you keep going. And this random walk was conceived a long time ago, but no one knew how to analyze it, because they were thinking of this huge graph where every vertex is a spanning tree, and you connect them if you have a move between every pair, like I said with the decks of cards. And this was just too hard to analyze. And what was the observation in this work? Don't think of this huge graph. Instead, think of a simplicial complex with much higher dimensional faces. The ground set will just be the set of edges, and the faces will be the spanning trees. So we don't just have triangles. You have faces of dimension n-1 or n-2, the number of vertices. And you move from face to face by erasing one of the elements and adding another element. So the top faces in your complex are all the spanning trees. And it turns out that you can analyze this walk very nicely by looking at kind of localized part, looking at links, and inherently inside your analysis, you're looking at all dimensional random walks. So somehow understanding that this is a high dimensional situation really helps the analysis go through. So, okay. So, and again, really what's happening in the analysis is that you break your random walk into small local pieces. Those are very easy to analyze, and then the global result just follows. It really, once you understand how to look at it, it really writes itself. Okay, so I guess almost last slide. There's been many interesting applications for high-dimensional expanders, from convergence of Markov chains that I showed you to many different things, new error-correcting codes, new quantum error-correcting codes, PCPs, a lot of different things, because these high-dimensional expanders have this local to global feature in a much more powerful way than just normal expanders. So somehow this turned out to be very useful so far, and hopefully it will find even more uses in the future. And for me, I think it's also just a very satisfying, beautiful connection between some interesting mathematics and some questions that I find very interesting. And I want to just point out this thing again, that all this area of high-dimensional expanders is based on some constructions in group theory or number theory that people came up with because of completely different reasons. I mean, why do mathematicians study group theory? They don't have necessarily applications in mind. They just want to understand, to find the truth, to figure things out. They're driven maybe by aesthetic reasons, like, oh, this looks beautiful, let's research this some more. And they have no end application in mind. And then maybe a century later, or maybe less, people find the applications for these things. So I think that's kind of beautiful. It's as if they, when you plant a tree, it takes many, many years for the tree to bear fruit. Sometimes it's way beyond your lifetime. And here you have this high-dimensional infinite tree that was planted for us, and now we have the fruit. So that's it.